This video will cover section 10.6, parametric equations. The objectives will be to evaluate sets of parametric equations for given values of the parameter. This may sound a little weird now, but you will see it's pretty easy. Second objective is to sketch curves that are represented by sets of parametric equations. And for this section, we're going to be working with two parametric equations. Also, to rewrite sets of parametric equations as single rectangular equations by eliminating the parameter. So we could go from 2 to 1. And the fourth objective will be to find sets of parametric equations for certain graphs. Everything that we have done up to this point, we have been working with two variables such as x and y. So in this section, we're going to study situations in which it is useful to introduce a third variable to show us how a curve in the xy plane will look like, and it will also include direction. So that third variable is going to be t for time, but you will see that in a minute. And to consider how useful this could be, consider the path of an object that is propelled into the air at an angle of 45 degrees. So having an object and then just being propelled at a 45-degree angle with the horizontal. And so when the initial velocity of the object is 48 feet per second, it can be shown that the object follows the parabolic path. And we have the equation here rectangular because we have it in terms of x and y. So that is rectangular. And so if we were to, same object, if we were to throw it, it will eventually reach a highest point and then it will come down. So that is the parabolic path that we're talking about. So with this equation, it could be the same as y equals -1 over 72 times x squared and then plus x. Remember here I'm just factoring out the fraction so you could see that very clearly that coefficient will be negative, and so that's how we know that the parabola will be opening downward. So if that equation doesn't tell the whole story of the object, and it could tell you where the object has been, but it doesn't tell you when. That would be the question, at what time the object was at a certain point, x and y. So the coordinates x, y, that will tell you the vertical. If we were to graph something like that, in fact, I'm going to just graph it on the calculator, or I'll just use Desmos. So here's Desmos, that is the URL. And all you have to do, if you don't have an account, you could create an account. You could sign up, you could use your Gmail or any email, and then if you already have an account, you can just log in. But if you don't want to create an account, it's fine. You could just go to graphing calculator. So we're going to graph that one, and it has, it says y equals and then I'm going to enter my coefficient in a fraction. So it is -1 over 72. And then I'm going to use my right side arrow to get out of the parentheses. Then I'm going to enter the variable, which is x, and then I want to square it. So no, this is a little tricky. Okay, I'm gonna pause the video and figure out how to type this. So I couldn't find how to do it with that keyboard, so I'm gonna try with the regular keyboard, and you use the caret symbol, which it will be like shift number 6, and then I'm gonna type a 2. You could see how the exponent is like a smaller quantity there. And then I'm going to hit the right side arrow to get out of the exponent. And then I'm going to enter the rest of the equation, which I forgot. It's here, plus x. So plus x, and then we press enter. So we could see the graph over here on the right side. And I'm actually going to zoom to change the graph a little bit so you could see it better there. And so considering that the object was thrown at a 45-degree angle, and so here will be the path of the object. This could be the horizontal axis is representing the horizontal distance, and the vertical axis is representing the vertical distance. So now for every single point on the path, for example, let's say here at at 40 feet horizontally, it was the altitude or the height was 17.778. So that's what tells us that. But we don't know at what time that actually happened. Now we know that right here it reached its minimum height. The height is 0, and the horizontal distance from where the object was thrown was 72, and I believe we were talking about feet. So at that point, we don't know at what time that happened. So that is one of the useful things of introducing the third variable, that we will be able to know at exactly what time that was the position of the object being thrown. So to determine the time, we're going to introduce the third variable, as we already discussed. We're going to use the variable t, the letter t, and that is what we will call the parameter. It is possible to write both x and y as functions of t to obtain the parametric equation. So here we have parametric equation 1 and parametric equation 2. And as you can see, the input for both of them is the variable t. That's what we say, they're both functions of t. That is the input. And the output is going to be, for equation number 1, the output will be x. So we call it, that is the parametric equation for x. And for equation number 2, the output will be y, and that is the parametric equation for y. So what we're going to do on the examples is how to find those two equations. Before we learn how to find those two equations, let's see what we will do with the equations. So for example, since now we have that t for time is our independent variable or the input, so at time 0, at the moment the object was thrown, it will be enough for us to substitute 0 in both of these equations. And after substituting 0, then we will get a point. and that will give us the position of the object. And so if I was to substitute both equations, substitute with a 0, this product will be 0, this product will be 0. 0 squared, 0 times negative 16 will be 0. So both x and y will be 0. And so what that tells me is that we will be at the point 0, 0, which is actually here at the origin, and both x and y were 0 when t was 0. So now if we want to know what happened at t equals 1, then we will do the same thing. We will substitute 1 in both equations. For every t, it will be a 1. And so after substituting 1, the points that we will get will be 24 times the square root of 2 for x and 24 times the square root of 2 minus 16 for y. So that point will be, I cannot see where that will be on the graph. So that point will be approximately 33.9411, and for the value of y, it will be 17.9411. So for the horizontal distance, will be almost 34. So, I don't know, maybe there, maybe a little closer to the maximum point, to the highest point, which is actually the vertex. And so the vertex is actually occurring at this particular time, which is the product of 3 times the square root of 2 divided by 4, and that is approximately 1.06 0, and then a couple of more sixes there. So at a little bit after 1 second, that's when the object reached its maximum height or vertical distance. So you see here we are using 3 variables so that we know the horizontal vertical distance of the object, but also the time. So that is one of the advantages of parametric equations. And so of course you could continue finding things, and if you know that the object landed 72 feet away from where it started, and the height was 0, as you can see here, that's why we say it landed. So to find the time, you could potentially take the 2 equations, and then in this case substitute x with a 72, and then substitute y with a 0, and then you will be solving for t. So if you were to do that, you will find that the time when that occurred was right here, which is 3 times the square root of 2 divided by 2. So I'm going to enter that on my calculator, and that is at approximately at the time 2.12132. So after 2 seconds, that's when the position of the object was 72 horizontally and 0 vertically. So like the distance was 0, meaning it was on the ground. So for this particular motion problem, x and y are continuous functions of t. A continuous function, you could see that they are both X is a linear function of t, which a line, they're continuous, and y is a function of t, and it's a quadratic function, so it's also continuous. So just so you remember, when we say continuous function, we mean those functions that have no breaks, no holes, and no gaps in between. And we have here the definition of plane curve. So it says if f and g, f is a function, g is another function. If f and g are continuous functions of t on an interval, and for that interval we just use capital I, then the set of ordered pairs f of t and g of t is a plane curve C. The equations, f of t is representing x, as you can see here, and g of t is representing y. So we're just calling them f and g so that we know that they are two different functions. And so when we say the order pairs, it could also be x and y. So instead of just saying x and y, we're calling it f of t and g of t, so that we know that they're both different functions in terms of t, meaning t is the independent variable. In this case of parametric equations, we refer to t as the parameter. T is the parameter because we're talking about parametric equations. And you can see it here, that's the input for both functions. So when we sketch the curve representing a pair of parametric equations, we still do it like we've been graphing, plotting points on the xy plane. And each set of coordinates, each point is determined from a value chosen for the parameter t. Remember, we did a little bit of substitution. So if we say let t equals 0, then we will go, and in both equations that we have here, we will be substituting, for every t that we see, we will be substituting the value 0. We might have like t squared like the other one. I think let's put a 16 there, so plus 1, something like that. So if we choose t to be 0, we will do that, and then if we change our mind and say, okay, let's let t equal 1, then we will go here, and everywhere where we see a t, we will replace that with the number 1. And after we compute those values, that's how we get our x and our y values, and those will be forming the order pairs that we have here. And we just graph it like we usually do. And it's also important to notice that since we're talking about time, t equals 1 will be after t equals 0. And so that also tells us the specific direction in which the curve is moving. And that is what we refer to as the orientation of the curve. So we have our first example finally here, and we're going to sketch the curve. And so for the table that we see here, I left the table there because it already has the answers, but we're still going to do the substitution like if we didn't have the answers, so we're just going to be checking. And you could see how here t it's been purposely we have already numbers assigned for t. So we have -2, -1, 0, 1, 2, and 3. So I'm going to work for the x values over here, and we have the equation. So we have t squared minus 4. So what we're going to be doing is we're going to be entering the value of t. I call this like kind of like the skeleton of the function, like where we're going to be substituting. Oops, no, got that. I want a square. And then we still have a minus 4. So when t is a -2, of course, we will put a -2 here. So it's going to look like this. X will be equal to -2 square minus 4. -2 square is equal to 4, positive, because -2 times -2 is 4. So 4 minus 4, and that gives us 0. So we have that one. We did it correct. Then we have for the next one, t equals -1. So that -1 will go there. But we have to use parentheses so that we don't forget. So -1 squared minus 4, that will be equal to 1 minus 4, which is -3. And that's how we obtain this value here. Let's find the next one. So now t is not -1. Now we want t to be 0. So we're going to put a 0 right there. So we're going to have 0 squared minus 4 is going to equal to 0 minus 4, which is -4. And that's what we have here. Let's do the next one. So x is equal to 1 squared minus 4. That would be 1 minus 4, and that is equal to -3. We have that there already. And now the next value for t will be 2. So we're going to substitute 2 squared minus 4, and that will be 4 minus 4, which is 0. So we have a 0. Finally, we have 3 here. So 3 squared minus 4, that will be 9 minus 4, and that is equal to 5. So that's how we substitute to find the values for x. Now on the right side, let's go ahead and find the values for y. So we have our equation here. We're just going to be dividing by 2. So we're going to substitute the value for t right here inside the box and just divide by 2. So the first value assigned, we start from the top. So it's going to be -2. So we're going to say y is equal to -2 over 2, and that gives me -1. We have that already. Next, t value is -1, so we're going to substitute -1 on the numerator divided by 2, so that is -1/2. We got it. Next, t value is 0. So we substituted that into the equation for y, so that will be 0 divided by 2, and that is equal to 0. So we see that there. Next, t value will be 1. So we're going to substitute 1 right there, 1 divided by 2, and we just leave it as a fraction because we want to have the exact answer. Unless WebAssign is asking you to enter an approximation, then you divide. If not, just keep the fractions. There's nothing wrong with them. So the next t value to substitute is a 2. So to find y, we will substitute 2 on the numerator, divide by 2, and that is equal to 1. So that's correct. And then the last one that we have here in the table will be 3 for t. So it will be 3 divided by 2. And that is just 3/2, which is like 1.5, but here we're just keeping them as a fraction. So remember, we substituted the values for t in here in the equation that was to find x, and also in the other equation, the one to find y. And now with all those values that we have order pairs. So those order pairs are the ones that we're going to use to graph, and you could see the graph is already here. However, let's go ahead and do this. So the order pairs are going to be those in terms of x and y, so they're going to come from here. So we're going to have 0, -1, we're going to have -3, -1/2, and we're going to have -4, 0, and we're going to have -3, 1/2, 0, 1, and 5, 3/2. So after plotting all those points, we could see the graph here. And with that graph, since we started with t equals -2, which will be right here. That was the first point that we calculated. That will be the initial point of our graph. Then, so that's the point that we have here. The point with the coordinates 0, 0, I believe. So I'm gonna try to bring these points here. It's not working. So let's see if this works. We're gonna move them so that we don't have to rewrite them. All right, so that will be the first point, 0, -1. Then the second point, and I'm gonna just copy the t values here. So this was for -2, -1, 0, 1, 2, 3. So we start from the smallest t value. That was the initial point. Then we had the next one, t equals -1. And here's our point, the one with the coordinates -3, -1/2. Then when t is equal to 0, right here, our point, you could see the coordinates -4, 0, and it's right here on the x-axis. Then we went to t equals 1, so right here, and the point was -3, 1/2. There we go. Then we have t equals 2, and the point is 0, 1, right here on the y-axis. And then finally, we found the one from t equals 3. And the point that we got from there, the coordinates were 5, 3/2, and that is the point that you see here. Now, the arrows that you could see here, those arrows are very important because they're also describing the direction from the initial point. And I mean, we could have more arrows here. From the initial point all the way to the terminal point. That was here. So it's important to know that the graph that we have in that figure, 10.40, does not define y as a function of x. Remember that we found each of them individually. We did that over here. They were both functions of t. And we found x and y individually, one at a time. So this points out one benefit of parametric equations. They can be used to represent graphs that are more general than graphs of functions. So two different sets of parametric equations can have the same graph. For example, if we were to graph this 2, remember finding points, all the x coordinates with this function. This is a function, x representing a function of t. Remember, we could also call it f of t. And the other one, it could be called g of t. So for both of them, the input or the independent variable is t. That's why we call them functions of t. And the output, it just happens to be, one is going to be x and the other one is going to be y. And when we put them together, they form an ordered pair. But we find those individually. So x is kind of like the new y, an output. Both x and y are the outputs of this parametric equations. So going back to the previous statement, um, we saw that graph came from this set of equations right here. And so if we were to modify them a little bit, or even just other equation, we could in fact find a different set of equations that will give us the exact same graph. So if you notice here, y was defined as t over 2, and for the other one, we're using y equals t. In fact, this is probably the simpler way to do it, unless, I mean, like if we had to find two parametric equations, this is the simplest way to just pick one of those and just say that equals t. So, that's the way to do it. And here we have the two graphs after calculating all the points. And you could see it's the same shape, and it does have the same direction because we have the arrows pointing in the same direction, as you see here. So however, the way that the parameter was selected for t, the values for t, was different. So for the equation on the graph on the left, the parameter was selected to be numbers from -2, including -2, to +3, including -3. So here we have interval notation, and this is just like using the inequality. Could also be used in set notation. For the other graph, the one on the right side, we have different parameters there. So we're actually going from -1 to 3/2. And so they are different. So right here, how do we eliminate a parameter? So we're going to use the same equations that came from um, example 1, so that you see how this will happen. So as we saw with the previous example, example 1, the way to find each point was a little lengthy, and because we had to find x and then find y based on whatever value for t. So it was like we were doing substitution for two different functions, and it's a little lengthy and tedious. So that's why we have this eliminating the parameter tool. So if we do that, we could arrive at just one equation, and then from there, we could just do some substitution once instead of doing it in two equations. So what we do is we follow the steps. So for the first step, you take your two parametric equations, and just like we did with example 1. Then on the second equation, because it will be easier, we solve for t. So if you notice here, the 2 is dividing t. So what we do is move it across, and it will be 2y is equal to t. So that would be step number 2. And of course, we could write this in switch the order. It's still t equals 2y. Then from here, the third step will be to go to the other equation. So in this case, we take the equation for x, as you can see here, and we substitute what we got for t. So you see that we say t equals 2y. So that's why instead of the t and the t square, we substitute that with 2y. Instead of having x equals t squared minus 4, we substitute that t for 2y. And after doing that, we have to, of course, use the exponent there. So the exponent gets distributed to the 2 and to the y. So 2 squared is 4, and then y squared is just y squared. So that's why we get that equation. And so that would be the fourth step, just to simplify it, simplify it into a rectangular equation. So now that after you did, I hope you already did your homework from section 10.2, which is the parabola. And at this point, you should know that we have those parabolas that open upward, downward, but also to sideways. So that is the equation of a parabola. And we call them horizontal parabolas because the horizontal axis is their axis of symmetry. And so for that parabola, the vertex is going to be -4, 0. So when you convert equations from parametric, remember parametric is when you have two of those, and you convert them you eliminate the third variable, t. So this is two equations. And when you convert them to rectangular form, you just have one equation, like that one there. So you may need to alter the domain of the rectangular equation, the domain of this one. So that it matches the graph, so that the graph of that one matches the graph of the parametric equation as well. So we're going to show you that on example 2. So in this case, we start with our two parametric equations right here. That's one, and that's the other. And what we're going to do is eliminate the parameter and then adjust the domain of the resulting rectangular equation, solving for t. Well, that would be the first step, actually. Solve for t in one of the equations. So we have t right here. We're going to solve for t. And in the equation x equals. So what's happening here is we're squaring both sides of the equation. So if we square both sides, we get x squared, like you can see there. And the square has to be distributed to the numerator, but also to the denominator. So imagine you have 1 square divided by the square root of t plus 1, and we're squaring that. So if we square square root, they cancel. So that's why we get 1 plus t. And then 1 squared is just equal to 1. So that is what we get when we're solving for after we square both sides of the equation. So from here, what we're going to do is we are going to, and I'm just going to continue to the right, and we're going to say that because t plus 1 is dividing the number 1, the only way to get that binomial out of there is by moving it to the other side, to the left side. So from division, it will go to multiplication. So we're going to have t plus 1 times x squared. And then on the right side, we just have a 1. So what I'm going to do now is, let's see, what should we do? We're going to take x squared to the other side. So now we have t plus 1 is equal to 1 over x squared. So remember, x squared was multiplying on the left, now it's dividing on the right. And then just finally, I will take the plus 1 that we see here to the right side of the equal sign, and it will be a minus 1. Now, the solution that you see here, it might be more convenient to work with. So to get to that solution, you will just have to change the number 1 so that it has the same denominator as the first fraction, x squared. So to do that, it will be enough to multiply the 1 by x squared, top and bottom. And so with that, we get x squared over x squared. So now that they both have the same denominator, x squared, we can combine them into one fraction, And so that's what we see here. 1 minus x squared on the denominator, and then x squared for the denominator. So now that expression that we got is what we're going to substitute for every t that we see in the other equation, like that. So first, we solve for t in equation number 1. Now we're going to substitute that expression in the second equation. So that's what we see on the next slide. And we have that, instead of the t, we have that expression that we found. And we have to substitute it for every t. Notice that we're still preserving the plus 1 here on the bottom. That it's here, plus 1. So one way to work this problem will be if we think that 1 has a denominator 1, and then we pay attention to our 3 denominators of the fractions within the fraction. We have this technique where you multiply by the LCD, both the top and the bottom. So if we do this, we will get to something that will look like this. So we'll have the x squared here multiplying this whole expression. So that will be 1 minus x squared over x squared. Then we will have also the other x squared multiplying everything that you see here. So it will be the 1 minus x squared over 1. I'm sorry, not 1. Oh, x squared plus 1. Okay, so if we multiply that, of course, we multiply numerators with numerators. So if we just write it this way, x squared times 1 minus x squared over x squared, you could see it's very obvious that the x squares will cancel out. So that's why we use that technique, multiply by the LCD over LCD, LCD meaning lowest common denominator. So if we multiply that x squared times the first fraction, it will be x squared minus, in fact, let's do this. Oh no. So x squared times 1 minus x squared over x squared. And then we still have to distribute that times the 1. So 1 times x squared, it will just be x squared. So here you could see it also cancels out. So now we have a very nice, well, not very nice, but a nicer fraction. From this part, we only have 1 minus x squared. And from the denominator, we will have, from this bottom part, we will have 1 minus x squared. And then we have the plus x squared. And so that will reduce to 1 minus x squared over 1, which is just 1 minus x squared. And that is pretty easy to graph. You could see that that will be the rectangular equation that they're mentioning here, this one here. And you can recognize that the curve is a parabola, and it's going to open downward because the coefficient of the x squared is -1. And the vertex is going to be at 0, 1. So the graph, I'm going to write it here. So it will be y equals this equation here. That will be the rectangular equation. y equals 1 minus x squared. So the graph for that, it's actually not what you see here only, but also on the other side. However, we don't need what's on the left side of the y-axis. We only need what's on the right side of the y-axis. And that is because the rectangular equation is defined for all values of x. The parametric equation for x, however, is defined only when t is greater or equal, only greater to -1. Let's see why. So if we were to put a number here in the first parametric equations, remember this is the rectangular after eliminating the parameter. So in the other ones here are the parametric equations. So to find the domain of, let's say, if we're working with y equals t over t plus 1, we know that if we had a value of 0 here, that wouldn't be okay because we will get an undefined value. So the way we find the domain in those cases is by taking the denominator t plus 1 and saying that cannot equal to 0. So that will be t cannot equal -1. Okay. So that helps, but now what about the other parametric equation? Because we have two. So if we take x equals 1 over the square root of t plus 1, to find the domain in this type of equations is the correct thing to do is to take the denominator, in fact not the denominator, but the radicand. That's what's inside the radical. So we take the t plus 1 and we have to say that must be greater than or equal to 0. And so if we solve for t, we could see that t has to be greater than or equal to -1. So the domain from the first parametric equation will be all the values that are either equal or greater than -1, including -1. However, for two reasons. Because if we had a -1 here for the t, we will have -1 plus 1 and it will be 0. And there's no problem. We can take the square root of 0. However, the square root of 0 is also 0. So from the beginning, I should have just eliminated the equal part of the inequality because the radicand is actually in the denominator. And so for that reason, we don't include -1, so we use parentheses. Another very good reason is that we cannot have t as -1, so of course -1 is not included. And you could see that by the fact that it's not included by the open circle that we have here. The circle is not filled in with black like the other circles that we see on the graph of the curve. So t must be greater than -1. However, you could still calculate what would happen at -1, but that point gets represented by the open circle that you can see here. That would just give you like a good starting point. So here you could see other values that they chose, t equals 3, t equals 0, and those are the points of the graph. For t equals negative 0.05, which is greater than -1, you could see it here. So that was a good start for it as well. So in example 2, it's important to realize that eliminating the parameter is primarily an aid to curve sketching so that you can sketch it faster. When the parametric equations represent the path of a moving object, the graph alone is not sufficient to describe the object's motion. So you still need the parametric equations, the one that is x equals and y equals, to tell you the position and the direction and also the speed at any given time. So you can get position from the two parametric equations. You could get position, direction, and speed at any given time. So now that we've been studying how to sketch them, now we're going to consider the reverse problem, and that is, how can you find a set of parametric equations for a given graph or given physical description? So from a graph or a physical description, and now we're going to have to find the parametric equations. So you know that, and you will see that those representations are not going to be unique. If you recall from what we did before, two different parametric equations can give you the exact same graph, as it was shown on a previous slide. So they give you the same graph. So let's go ahead and get example 4 started. So we start with a rectangular equation, and that is here. And the question is, find the set of parametric equations. So you already know that what that means is we have to find something of x equals and y equals, and they're both going to be functions of t. T is the input. So we start by using the easiest substitution ever, which will be let t equal x. And we say that so that we could just substitute into the rectangular equation that we have here, the x. And so if we let t equal x or x equal t, then the equation that we have here, we will say y equals 1 minus, substitute the x with a t, so t squared. And that's how we obtain our two parametric equations. So it's that simple. Now I also could have said let t equal 2x, and then say x will equal t over 2. So in that case, I would have substituted x squared here with t over 2. But of course, we're always trying to, not work too hard. So it's perfectly fine if you decide to just substitute x with a t. Now, this is another example. We could say now, well, we want to let t be equal to 1 minus x. So now with the same rectangular equation given, now this x squared will get substituted by the whole expression 1 minus t. So you could see here the x squared substituted with 1 minus t. And with that, you need to be careful because 1 minus t squared, it means 1 minus t times 1 minus t. And so that will be 1 minus t plus t squared. And that is equal to 1 minus 2t plus t squared. So with that, if we have, and right here, they're kind of like skipping that step. So the step in between there will be, we have this one, first of all, And then we have the result of this substitution, which is what I have here. Oops, not like that, but here. So I'm going to replace all of that there, but I'm going to leave it in parentheses. So it's going to be 1 minus 2t plus t squared. So after distributing the the negative sign that we see here, this will be 1. We cannot forget about this 1. So it will be 1 minus 1 plus 2t minus t squared. And of course, you can see clearly this 2 will cancel out because they're equal to 0. So the solution is right here. So that's what we have here. I just wanted to make sure you understood every step. And now for that, now we have a different set of two parametric equations. One will be what we started with by letting t equal 1 minus x. So if we solve for x, then we will get our first parametric equation. Then after substituting that expression, 1 minus t, we were able to find our second parametric equation. And if we were to graph them, both of those will give us the same graph. And you can see that there. So a cycloid, for example, 5, it's a curve traced out of by a point, let's call it P, on a circle as the circle rolls along a straight line in a plane. So to write parametric equations for a cycloid traced out by a point on a circle of radius A as the circle rolls along the x-axis given by P is at a minimum when x equals 0. And there is an image coming up that will make more sense. So as the parameter, let theta, instead of t, we're going to use the parameter theta. And that will be the measure of the circle's rotation. Let the point x comma y begin at the origin. So if theta is equal to 0, then theta will equal, oh, sorry. If theta is equal to 0, the point will be at the origin at 0, 0, right? But now if we let theta equal pi, then the point that will be matched with it will be right here. So x will be pi a, and then y will be 2a. So, and if we let theta be a third value, 2 pi, and we substitute, then the point that we get is 2 pi a comma 0. So we have the point 0, 0 at theta equals 0. We have the point pi a comma 2a at theta equals pi. And then we have the point 2 pi a comma 0 at theta equals 2 pi. And here is the image that will be at theta equals 0. Here is what's happening at theta equals pi. And no, actually, I think I'm wrong. I need to check. Yeah, it's here at theta equals pi. Right here, that's the x coordinate of the point. And then this last one is when theta equals 2 pi. And remember, the point that we get from there is there. So that's why we see it on the x-axis, because the y value is 0. This is the highest point. And that's the path that we will be tracing if X and Y were just positions for a particular angle, and that's the parameter as the circle is rotating. So for this cycloid, the two parametric equations are the ones that we see here. Those are the parametric equations. So since we have the parametric equations there already, we're going to use them here. So for sine, recall that we know that for sine and cosine, and so the last slide, it is the explanation of how the two equations, parametric equations, were found with respect to the rotation of the circle here. You could also see how the angle, they're referring to the angle APC. So that will be the angle that starts at point A and then goes to point P and then C. So we're talking about this angle here. So that angle is going to be defined as pi minus theta. And we say theta, pi minus theta, because you could see here you have a right triangle. And so if we have a right triangle already here, one of the angles is 90 degrees already. We know the interior angles of a triangle are 180. So if you already take 90 out of it, you have the other 90 to work with. Now here, what we are assuming is that we are going to have 180 minus theta. So right here, the angle APC, that was the angle that was coming from pi minus theta. So you can see the substitutions here. The sign changes if we use pi minus theta to of cosine, it changes to negative. And so here's how they derive by using segments and values for A. So remember, the capital letters will be giving you the segments, and then the lower cases were used here for the points. So after we simplify those operations, and here we have it in terms of OD minus BD, and that is A theta minus A sine theta. Here we have BA plus AP, and that is A minus A cosine theta. And that is just how they found the equations. The final ones, you could see how A was substituted from the Y. So we get A times 1 minus cosine theta. And for the first one, we get to substitute, factor out A. So then we get A times theta minus sine. So this is the end of the video.